let's think a little bit about what we mean by the derivative of a vector function. We've seen how to calculate it. We've seen what it means, or at least we've asserted what it means in the case of a vector function that represents the motion of an object. But what does it mean in general? Okay, I've only sketched this in 2 dimensions, but the sketch could equally well be done in 3 dimensions. We could have 2 vectors with any orientation in 3 dimensions. Let this vector represent the vector function f at clock time t, or at value of the parameter. T doesn't necessarily have to be a time parameter. And let this vector represent f at what we would think of as a later time t, or t plus some small increment of t. Okay, so that f changes between here and here. Now, let's think about what we mean by average velocity. Okay, the average velocity of an object is just the change in its position divided by the change in its clock time. And if its position is a vector, that's all right. We can divide the change in a vector position by a change in clock time. That's not a problem. We get a vector that's parallel to the delta f vector, but the division by delta t changes its magnitude and its meaning. Now, delta f, in this case, is just going to be the vector from the tip of f to the tip of f of t plus delta t. That's the change in the vector function. Okay? And that's, of course, what we get if we subtract f of t from f of t plus delta t. So our delta f is just this difference. It's the difference from this vector to this vector. And that's the vector from the tip of the first to the tip of the second. Delta t being the time interval, we don't know how quickly this occurs. We don't know what the delta t is, but whatever it is, we're going to divide that delta f by that delta t, and we're going to get a vector that we call the average velocity vector. Delta f will be some displacement in some direction. It's going to have a magnitude and a direction. We divide that by delta t, and we get the average rate at which f changes with respect to t. Whatever the interpretation of f could be a force and t could be something besides clock time. T could be a position along a line or something. Okay? Now, what we mean by the derivative of f with respect to t is just the instantaneous rate of change of f with respect to t. In the motion interpretation, this is going to be the average, or the instantaneous velocity. And what we mean by instantaneous, and you should know this, of course, from first year calculus, is as we shrink the value of delta t, we get a smaller and smaller delta f, but we also are dividing by smaller and smaller delta t. Now, when we shrink the delta t, the direction of this thing might change a little bit. We don't know what kind of curve this thing is following, but the direction of this will always be a secant across the curve. So, for example, if the curve looks like this, if we choose a smaller increment, then the direction from this point to the other point of the curve is going to change somewhat. If we're using very small values of delta t, of course, the path will eventually appear pretty much straight between these points. And we'll be approaching the instantaneous velocity at this point. which is the limit as we get closer and closer to this point of the change in f divided by the change in t. So we're going to approach the instantaneous rate of change, and that is the limit as delta t approaches 0 of f of t plus delta t minus f of t divided by delta t. And we represent that by our derivative. If we take a closer look at what happens in the vicinity of this point, now what I've done here is we just consider this to be the end of a vector that starts somewhere way back off the paper, and this is the end of the other vector, again, that starts way off the paper. We observe that the change delta f can be expressed, and sometimes it's important to do so. This can be expressed as the sum of the change in a direction, the component in a direction perpendicular. So we're going to call this delta f perpendicular, the component perpendicular to f itself, and a component that I'll draw here, delta f parallel, so that delta f equals delta f perpendicular plus delta f parallel.